Dear friends, Maths Aspirants is a collective of mathematics students, research scholars, faculty members across India, started by myself in 2017. And we used to organize several online programs to help the students. As a part of the online problem solving session series, today we blessed to have Mr. Aviral Srivastava. He is currently pursuing PhD at IIT Gandhinagar. Mr. Aviral did MSc from University of Hyderabad, and he qualified IIT JAM examination, CSIR-UGC NET, and GATE examination, and also NBHM Doctoral Fellowship. So I'm very proud to introduce Aviral to all the participants. Actually, he is a active member in our Maths Aspirants group, and also had conducted some online problem session in our platform also. So today he will discuss some selected problems from real analysis, especially focusing on IIT JAM examination. So I welcome everyone to this program. Welcome, everyone.
Okay, thank you, sir, for kind introduction. And so today I collected few problems from this IIT JAMs, mainly from previous year question paper. Actually, there were a lot of problems. I tried to collect it from past 4 years because I gave my IIT JAM in 2020. So I thought, why not let's see how in the last 4 years things went. So I tried to solve those problems and tried that so that I can also get hands on some new problems and all. So it was a good experience. But there were a lot of problems. I couldn't decide which one is good to pick, which one was bad. So I picked some questions randomly. I will try to present them. In case you people find some mistakes or something, please feel free to stop me and point out the mistakes. I actually couldn't got a lot of time to prepare them, but I tried my best to prepare. Still, if you find some mistake, please feel free to tell. Okay. So let me start with this problem. So this is the first problem we are going to do. So we have given a continuous function from closed interval 0, 1 to 0 to infinity. And we have given some condition on this continuous function, which is given by which is given by which is given by ft of square less than 1. So this is the condition given to us, and it holds for all t belongs to 0, 1. Correct. Now what we need to find is to find a bound, either upper bound or lower bound on ft, which holds for all t in closed interval 0 to 1. So what is the idea? So basic idea whenever we try to find the lower and upper bound is mostly to use the derivatives. But how to use the derivative? This is the trick here. Okay. So let me take GTS function. This. So first thing to note is that
Hello, Aviral. Your voice is
yeah.
not hearing properly.
Okay. Wait. Just a second.
Okay.
Is it
Now
good
it's
now?
okay. Now it's okay.
Okay. So we have is it good now, right?
Yes.
Hello.
Yes.
Okay. Okay. So we have given this g raised t equals to 2 times ft, and moreover, since we took our gt as this, and from here it implies that ft is ft square is less than or equals to, not less than equals to gt. Correct. So this quantity will be also less than equals to 2 times root gt. Right? Okay. So till now we are good. Now what will I do? Now let's see this. Okay. There is some quantity. We know that gt is differentiable function and root of gt is also a differentiable function. So what we'll do, we can find some by which is lying between t and 0 such that this thing hold. Can somebody point out why it should hold? Anybody?
Mean value theorem.
Yeah. So we should have this because of the mean value theorem. Correct. So now we'll do the derivative, which turn out to be correct. Now from this equation, let me call this 1, and since this is holding for all t in this interval, this quantity will be less than 1. Correct? Because derivative of g is strictly less than 2 times root of gt. So g dash by over 2 times root of g by should be strictly less than 1. Correct? Now this should imply that root of gt should be less than t plus root of g0. But I already mentioned that g0 is 1. So this, yeah. So this, did I did some mistake? Yeah. So it is good till now. So root gt should be less than equals to t plus 1. Correct? Now again we can use equation 1 and put this value, and we'll get this, and this will imply that ft should be strictly less than t plus 1, and this should hold for all t because all the steps are holding for all t. Any doubt? So this option is correct. What is the trick that we did? Because this only inequality is given, right? And
Excuse me, sir.
eventually, yeah.
So can you please explain the last part, where root of g of t and how that f came in?
Yeah, sure. So let me call this second, okay? Now using first, I can replace this root gt with this inequality, correct? This. So I just by using equation second, this root gt is strictly less than t plus 1. So I replaced in the inequality first, and I got 2 times ft should be strictly less than 2 times t plus 1. Correct?
Yes, sir.
Okay, good. So we got ft strictly less than 1 plus t, and that's it. We got the answer. You may ask, I mean, that how all of a sudden I got this trick and all. One basic thing that we learned, or you must have observed, that whenever we need some inequality on the function, for instance, you must have proved that e raised to x is strictly less than 1 plus x, or some inequalities of log, or some inequalities of sin x. For instance, sin x is less than x for x greater than 0. All such things we use mean value theorem most of the time, and we required the bound on this quantity so that we can bound ft, and hence we took this function as gt, tried to bound this function gt, and then we got the bound on ft. This is the main intuition that you can think of. Otherwise, to tackle these kind of problems, it could be all of a sudden could be difficult, but this kind of insight may be required. Okay, so let's move on to the second problem. So second problem is, we have given that F is a bijective map such that this is this series converges, right? How many such bijective maps are possible such that this kind of series converge? So let's see. One straightforward intuition you can try is that Fn equals to n. Fn equals to n is one of the bijective maps, very trivial bijective map, and but this example leads us to this, which is harmonic series, but this is divergent, correct? So kind of intuition you can generate that it may not be possible to have it convergent for almost any bijective map. Let's see. So first of all, since F is a bijective map, so what I can do, I can bound Fn, because it is 1 1, right? So this should be a term, and moreover, since it is a bijective map, and one should note that limit n goes to infinity, Fn should be equals to infinity. Why? Because if it become bounded somehow, then you won't be able to map all the numbers, correct? So it have to be going finite, infinite, I mean. And in case it is going infinite, it have to be increasing, because suppose it went to 5,000, some term 5,000, and then it start decreasing from there, then it won't be able to map numbers that are greater than 5,000. So this kind of thing is there. So hence, first of all, we know that it should be increasing, correct? Now, using this, we know that Fn should be less than equals to Fn plus 1 plus 1, at least the difference of 1, because we are dealing with the integers. So strict inequality means at least Fn plus 1 is greater than Fn by just at least by one number. And similar kind of thing will work in for all other numbers, right? And keep going, we will have please ask me if there is any doubt till now.
Sir, what if the numbers, I just swapped each corresponding numbers? Like instead of writing 1, 2, 3, I'm writing 2, 1, 4, 3, like that. Then this
Yeah.
inequality may not hold.
Yeah. Okay, so let me I got you. So let me write this. Yeah, I got you what you're saying. So there exists some n naught such that after this certain n naught, this inequality will hold. Now this is correct, right? You can swap till a finite number. After that, it have to be increasing. No other choice, isn't it? Otherwise, you won't be able to cover the whole set of infinite numbers. Okay. So now in this case, suppose Sn equals to this partial sum. This partial sum, and now we'll show using Cauchy's theorem that such a series will diverge. So we have this partial sum. What we need to show that this partial sum will not follow the Cauchy's inequality. So let's take this term. this will become and now this is greater than or equals to, because each of these terms in the denominator are less than m plus 1 square, so this will become this. Is it correct? This inequality? Right or not? Okay. Am I still on the call? Oh, okay. So this quantity also, using this inequality, this will imply f of n plus j is greater than or equals to fn plus j. Correct? So I can write all these terms as follows. Is everybody clear with this inequality? Okay. So again, this is greater than. So if I sum it, so it is not actually greater than at this step, it is just an equality. So we have m times fm, and this will become m times m plus 1 over 2 whole upon m plus 1 whole square. Correct till now. Although I need not to put this mod, because we are still in positive numbers. So this quantity is greater than or equals to times correct. Is it correct?
Yes, ma'am.
Okay. Now, because this is some finite quantity, and this term is greater than 0, because we are dealing with positive numbers, so this term is greater than 0, and you can see this, that m over m plus 1 is always greater than or equals to half. Correct? Right? Yeah. So this is greater than or equals to half, so this quantity is strictly greater than 1 by 4. So what we got? We got s of 2m minus sm is strictly greater than 1 by 4. And when it is valid for whenever m is greater than n naught, because we need to take sufficient large enough terms to avoid that swapping that somebody was saying, and any kind of repetition that could happen possibly. So because of that, we need to take sufficiently large term. So for sufficiently large term, we get s of 2m minus sm is strictly greater than 1 by 4. Correct? Now, does that contradict Cauchy's theorem? Exactly. So we can take epsilon less than 1 by 4, and for this epsilon, we have no say capital N, such that so okay, I can use this. Okay, this is the condition for convergence of Cauchy, and we know that if it follows, it will be convergent, and otherwise it will be divergent. So we got this inequality, and if I take epsilon to be less than 1 by 4, then for this epsilon we have no capital N such that this inequality follows. Because if there is some, then we can take our m to be large enough to surpass that capital N, and again this inequality will hold, which is s of 2m minus sm strictly greater than 1 by 4, which will again contradict the Cauchy's equation, right? Okay, so that's it for this problem. So number of such bijective maps, there could be no one, so the option B is correct. Yeah, I don't know, I can, oh sorry, this
Sir.
B1 is correct. Hello,
Sir,
hello, am I audible?
sir, we finally got that there is no such bijection, right?
There is no such bijection. What? Yeah, yeah.
If I choose a bijection that every odd number is mapped to even numbers, like if n is odd, is mapped
Yeah,
to 2.
yeah. Wait. So what you're saying? You are mapping 2m to what? 2m plus 1.
The idea is if I map every even numbers to odd numbers and every odd numbers to even numbers,
Yeah.
then even after any stages, we can't get any increasing sequence, right?
Wait. Yeah. So you're saying that so 2m goes to 2m plus 1, right? So okay. Wait. So for instance, let me take fn such that this will go to n plus 1. Is it you're saying or what? I didn't get. If n is odd, right? So if n is odd, I can write map it to n plus 1, which is even, right?
Yes, sir.
Yeah. So isn't it an increasing sequence?
Oh, yes, sir.
Yeah.
Yes.
Yeah. So it will be again increasing, right?
Yes, sir.
Yeah. I mean, did I get your question right?
So if n is odd, then fn is mapped to n plus 1.
Yeah.
So
And
if
if n is even, then where I should
up to n minus 1,
n minus 1 should I? Okay. Can you explicitly tell me the map? That would be better.
actually I don't like if n is even, we just map to n minus 1.
Okay. Okay.
Then if
So
what?
no, I got your question that you are saying that if we make it like this, it may not increase, right?
Yes,
But
sir.
I think it is increasing, but still I need to check.
Okay, sir.
Oh, so F1 is okay. So F1 is 2 and F2 is 1. Okay. And then F3 is 4 and F4 is 3. Oh, okay. So it is kind of, yeah, I got it. Yeah. Maybe I did a mistake. So it is first decreasing, then increasing, then decreasing, then increasing. You're saying, right?
I just asked you if it is
It,
a possible.
yeah, it is possible, and this is the map possible. Okay. Yeah. So I should have took the subsequence. I'm very sorry. Uh, I did this mistake. So instead of okay, wait. Let me rephrase it again. So what will happen in this case? this is fine, but again you will get a subsequence. So for instance, I can get a subsequence this and this and this and this. Okay, so rather I should have said that we will get a subsequence of this bijection which will be increasing. I mean, the intuition was to say that if it is not increasing, then it can't go to infinity. Okay, so that was my. I mean, at least one of the not the sequence, at least one of the subsequence should be increasing. Because if none of the subsequence is increasing, then we will have the trouble, right? So okay, so I should have rephrased it, and instead of, okay, maybe I will go I will finish other problems, and then I will come back and correct it. So instead of taking this kind of sequence, what we need to do, we need to take kind of J1, J2, and some, okay, KJ. So this kind of, sorry, JK. So this kind of subsequence we need to take now. Yeah, you pointed out it correctly. So it may happen that it increase, decrease, increase, decrease, and keep going. So instead of taking the whole sequence, we can pick out a subsequence which is increasing, and then we can proceed exact same idea, and which will give us the inequality on, again, on the subsequent, and which will again tell us that the Cauchy inequality is not holding. Is everybody on the same page now? I mean, is idea clear? In case it is not clear, I will come back and rectify it. I did the mistake actually, right? Hello, sir, should I move on?
Yeah, yes, Aviral.
Yeah, okay.
You can.
Yeah. I'm sorry for the mistake. Actually, yeah, I should have thought it, but yeah, so we can take a subsequence, and the proof will not alter much. But before I move on, I will just give a exercise to you people, that suppose if I remove the condition that it is bijective, suppose I just say that it is surjective. Can we find a surjection such that this sequence, this series converges? Okay. So think about it. I tried to build a surjective map which will converge, but in case somebody think about this, let me know. I will send that sequence. Okay. So we have next problem. So this is about the limit of a sequence. So let's see this. So we want to find out this. Okay. Now, to see the idea, let us call Sn as and with this Sn, we wanted to find limit n goes to infinity Sn, correct? So let's modify it, and it will turn out to be a some different expression. So what we'll do, we'll basically apply a square minus b square equals to a plus b times a minus b, which turn out to be this. Okay, and this will become 1 by 2 times 3 over 2 times 2 over 3 times 4 over 3 times 3 over 4, and keep going. And if I write the second last term, it will turn out to be n minus 2 over n minus 1 times n over n minus 1 times n minus 1 over n times n plus 1. There is the second last term. Okay, there is the second last term. So is this clear to everybody? So simply we can cancel out the terms, and okay, yeah, so we can cancel out the terms, and we're left with, so this term will cancel out what the previous ones, and we're left with half of n times n plus 1 over n. So basically our Sn became this, and now applying this limit, this will become 1 plus 1 over n. Can somebody tell me, if I go n goes to infinity, what 1 by n will go to?
0.
0. Okay, good. So it should be half. Okay. So this, I guess, yeah, so this A should be correct. Okay, let's move on. Now we have this problem. Again, this is kind of, yeah, finding a limit of a sequence. So let me call it, again, let me call it this. This, but this summation is but this upper term is independent of the summation, so we can take it out because it is independent of n, I mean independent of k, and we can leave over this shit. Okay, now thing is, this series actually converges. So what will happen, so this summation, can somebody tell that if I take n goes to infinity, can this series converge or diverge?
Converge.
Converge. Okay, so it will converge, but we don't, I mean, we can show it using this integral test. You can see this, the series is of positive terms as well as decreasing. So we can apply integral test, and I can apply this inequality. I can take one term out plus rest of the integral. In case somebody is wondering that why I did what I did, so I mean, you can always bound your infinite series using a triangle. So what you do, you take the first term out, and rest of the thing you take the integral with the first term, and this is the very standard inequality. You can find it. So basically, when we try to prove this integral test, we encounter this kind of inequality. If you see the proof of integral test, you will see this kind of inequality, which turn out to be then which turn out to be the theorem. So okay, this is the thing. Now if I integrate it,
Sir,
what will, yeah,
sir, as k goes to infinity, we know that log of k will also go to infinity, right?
no, what k is not going to infinity, right? N going, yeah, tell, yeah.
So then k over log of k, that will also go to, that k into log of k square, that will also go to infinity.
Yeah,
So okay, then we get the limit 0. That's why we have to check for the limit test. Oh,
yeah.
got it, sir.
So this log 2 square plus. So this integral, if I just substitute by equals to log t, then it turned out to be okay. So by substituting by equals to log t in the second integral, in the integral term 2 to infinity, we will get this, not log 3, it should be log 2. I'm sorry. Yeah. So it is going from log 2 to infinity dy over by square, and which is nothing but this term. Okay. And this is log 2. I'm sorry. Got it. So this term is bounded. Correct. This term is bounded, and now we can do one trick and we are done. So what happens? This correct. I just multiply and divide by this term. In the numerator, I will get 1. So using this and this bounding fact, we can have this inequality and let me call this constant as c, and you will get c. Okay. Now what we need to use to prove this? Can somebody point out? Sandwich theorem, right? So sandwich theorem says, because I can take my fx to be 0, gx to be this term, and hx to be the thing that is given. So you take this to be hx. Okay. And then by sandwich theorem, it is easy to see that limit n goes to infinity, this term will go to where? Tell me. It will go to 0, right? So this is the correct option. Is there any doubt? Okay, I suppose there is no doubt. So okay, so let me move on. So here is this kind of power series is given, and we are asked to find out f of half. Okay, so let's see this. Okay, yeah. So we have this power series, which is actually given by n square. Correct. And this is our fx, and we are asked to find out what is f of half. Okay. Now we'll use the series of log to do this. And note that x is given in the range of x less than or equals to 1. So there is no such confusion about convergence or something, right? We can write this, correct? So this is the power series of log, and what we can do, then log of 1 minus t become negative of because all the terms will turn out to be negative. And then just okay, just take out one of the t's, and we still have this. Is everything correct till now? Any doubt? Okay. So this is the power series of log of 1 minus t over t, and this summation is this. But what we required the series of something of the kind x raised to n upon n square. What we need to do now? We can integrate, and using the integration we can take one power in the denominator, and which will do our work. And integration is allowed under the summation just because of uniform convergence of the series inside the interval -1 to 1. You can just verify it. So uniform convergence allow us to take our integral inside, and I can integrate here also 0 to x, 0 to x. Correct? And now this turn out to be integration will give us t raised to n over n square dt. And this is the series that we were looking for. So this series will become, okay, so I'm sorry, it should be x, yeah. So after integrating, the 0 term will vanish. So this will become this, and we'll get over t times dt. And now we are, this was our fx, right? So this was our fx, and we were asked to find what is f of half. So f of half will become 0 to half log of 1 minus t over t dt. That's the answer. Correct? And the option which is correct is this B. Okay. Can somebody just, can somebody point out if anything is there? Or just say if I'm audible or not audible?
Yes, sir, audible.
Okay, thank you. Actually, I don't get the idea if I'm on the call or not because of some network issues. Okay. Let's go to next question. So next question is, so in the next question we have given two sequences, and we are asked to about the series that they form. So an is given as log n plus log n raised to log n, and bn is given as n raised to 1 plus 1 over log n, and we are asked to find out the convergence of 1 over an and 1 over bn series. Okay, so let's go with the first one. So we have given an as log n plus log n whole raised to log n. Okay, and we need to find n greater than equals to 3 raised to log n. Correct? So this is the thing we need to find out if it converge, diverge, or whatever, what happens. Okay. One thing that I would like to do first is to take some terms out that will ease our job. So I will take out this log n outside, and rest of the terms will become 1 plus correct. Okay, but we know that is greater than 1. So because this term will be positive, so this will be greater than 1, or maybe we can call greater than equals to 1. So this series n greater than equals to 3, 1 over log n over log n times this term should be less than or equals to this thing. Correct? So we use this inequality that this term will be greater than or equals to 1. So reciprocal of this will be less than or equals to 1. And hence this series can be bounded by this series. Okay. Now we are left to find out. So we will be done if we prove that this series converges. Correct? We need to see that if this series converges or not. So first of all, again, it is a series of positive terms decreasing and tends to 0 as n goes to infinity. And by the hypothesis of condensation test, I hope most of you must have heard about Cauchy's condensation test. So this series follow the hypothesis of Cauchy's condensation test, and you can see that, and so we can apply Cauchy's condensation test that will allow us to say that this series converge if and only if this series converge. Okay, correct. And I should write using Cauchy's condensation. Test. All right. So we are left to see this series. 2 raised to n, and this n will come out this, and again this n will come out of this, and this will become log 2. Okay. Now what we'll do is that n times log 2 times log 2 is actually greater than 2. Correct? Since it is greater than 2, so we can write this series as okay, so I meant to say is that we have in the denominator this in the numerator this term, and the denominator this term. Okay, and the growth of it is of the order basically n raised to n. Correct? And the growth of this term will be large enough to overcome this, and hence this series will converge. Even if you don't satisfy by that, we can simply apply that nth root test. So what will happen in nth root test if I pick out this series? Correct? And we take nth root of this. This will be 2 over n log 2 times log 2. Now as n goes to infinity, so as this limit goes to infinity, this will be 0, which is strictly less than 1. And by nth root test, this series should converge. So I can say n1 converges using root test. Correct? So what happens? This series will converge. Okay, so let me use some other pen. Okay, so this series will converge if and only if this series will converge. Correct? And then we have this series, which is just same series only, and we know that this series converging. So this series is basically convergent, and hence we have this series convergent, correct? And which points out that the original series that we begin with is convergent just because of the inequality. Okay, so let me call this second, and so using second and the fact that please feel free to ask any doubt, because I use too many series in between and inequalities. In case you get lost, please ask me. Okay, don't be hesitate to ask. Okay, so feel free if you stuck somewhere. So this is how we have done. We proved that the original series can be bounded by some series of the kind 1 over log n raised to log n. And then we proved that 1 over log n raised to log n is convergent using Cauchy's condensation, as well as we used root test. And hence the log n over log n series will log n raised to log n series is convergent, and by inequality the original series is convergent. Now we know that 1 over n is convergent. Okay, only thing is to left to check is 1 over bn case. So bn was given by n raised to 1 plus 1 over log n, and we are asked to prove about this thing. Okay, now what we can do in this case, again we can apply Cauchy's condensation. In fact, in this case we can apply comparison test also. So better apply comparison test, that to limit comparison. So this 1 over bn is nothing but 1 over log n, and compare with, so our test series is summation. So our test series is with this coefficient. So test series is 1 by n, and using, so let me take it maybe cn. So we know that limit n goes to infinity, cn over bn is nothing but 1 over n raised to 1 over log n, correct? And now we need to see where it goes as n goes to infinity. So I will left it to for you to check that this is 1 over e. Okay, it is very easy to check that this series tends to 1 over e as n goes to infinity. And now because this is a finite number, so the behavior of series cn and bn will be same, but summation bn diverges. Why summation bn diverges? Can somebody point out some test why harmonic series is divergence? Anybody?
Ratio test.
Yeah, you can say ratio test, but we use p test, right? Most of the times.
PC.
Yeah, p test. So hence cn diverges. So basically this series 1 over bn diverges, and we have first option correct. Okay, got it? So we proved that this series summation n greater than or equals to 1 over bn diverges by comparing it with harmonic series. Okay, next problem. Okay, so this is the problem of again sequence and series. So again we need to find out the convergence and divergence. Okay, so in this case, we have n equals to p raised to n times n raised to q times n over n plus 2 raised to n square. Correct? Now, uh, uh, we have a lot of n powers there, you can see, and one can be easily tempted out that, yeah, we can apply this root test because it will take 1 over n. So let's see, if we apply root test, what will happen? We need to find the convergence or divergence of this series. Now, let me take nth root. It will become p times n raised to 1 over n q times, and it will become, and note that we require conditions on p so that this series convergent or divergent. So in the first case, we require condition on q and p, and in the second case, we require condition on r. So in first case, we are doing using nth root test, and we get this. So when I take the limit, okay. So can somebody tell me quickly what this is? I mean, standard series that we learn. So can somebody point out where this series tends to?
P by E square.
What?
1.
1.
1, right? Yeah. And where this series tends to?
P by E square.
Yeah. So 1 over e square, right? Correct? Oh, sorry. It should be, yeah, 1 over e square. So we'll get as p times 1 over e square, correct? But by root test, this limit should be less than 1 for the series to be convergent, correct? Okay. So we got p to be less than e square. So this is the condition on p to get the convergence. So p should be less than e square. And if q is greater than 1, I don't think there is any such role of q. So if q is greater than 1, we are fine with that, because ultimately this n goes to 1 over n will tends to 1. So any power of 1 will be 1 itself. So it doesn't matter. So whenever this condition hold, and in fact we can take any q. So but in the question it is given to be q greater than 1, this series convergent. So and by the way, I forgot to tell you, in I put the questions in the series. So all these are MCQ questions. Then we will have MSQ. Then we'll have numerical types. So in that format, I've stated the question. So we got the condition this, correct? So this is the condition that when n should be convergent. And now yeah, and now what we are left to see. Okay, so this is one option correct. So we know that all other options are incorrect, but still let's check for the bn also for just kind of clarity. Okay, so for the bn case, again we'll apply nth root test. So bn is given by, okay, Now again, applying nth root test, we'll have n raised to n upon n factorial to 1 over n times 1 by r and times nth root of this quantity. And intentionally I have kept n raised to n and n factorial together. You will see why. So we need to find out this limit quickly. And this will become 1 plus 2 over n raised to 1 over 2n. Correct? Now, and we have 1 over r here. We need to find out first this limit. And here we'll use a concept of a limit infimum, limit supremum, not exactly, but I will just mention a result which help us finding such a series. So result is that actually there is inequality of this ratio and nth root. So let me just write quickly in case any one of you are not seen this. And this holds for any sequence. Which is less than or equals to. So what it imply actually? So this imply if
Sir,
exists.
at the end it should be limit supremum of an plus 1 by an, right?
Yeah. I'm sorry. Yeah, correct. Thank you. So it should be limit supreme, not infimum. Okay. So this says actually if the limit an plus 1 over an exists, then limit infimum, limit supremum are equal by concept, and then the series inside should exist. Then this series, sorry, not series, this limit exists and equals to okay. So this is the concept we will use. So we have this term n raised to n, and this is nth power. So it is sufficient to see if where the ratio, if we in case we get the ratio. So we will use this result. Okay. So just to see this ratio, we are left to do this, the n plus 1 term which is inside the bracket, and then it is n factorial upon n raised to n, which is upon the nth term. Is it correct? And I mean, I am yet to verify if it exists, but I know it exists, so I just equated it. So this is nothing but limit n goes to infinity, and it will become n plus 1 raised to n over n raised to n. And can somebody just quickly tell me what is this converges to? E, right? Eilers constant. So this is E, and series inside that is the limit 1 plus 2 over n 1 over 2n. This will also converges to what? E. Should I tell how I'm getting it, or is it fine? I hope, I mean, I hope many of you must have seen this. It is just, I mean, one, is it fine? I mean, hello?
Yes, sir, it's fine.
Yeah. So, okay, so it will become, so product of the two series become e square, so limit goes to infinity, 1 by m equals to r time, oh, I think, just a second. Yeah. Just a second, okay. Okay, so we require bn to 1 by n, and then it turn out to be, yeah, so it will become r is in the denominator, and the numerator we got e square, correct? Yeah. Is that fine? Okay. So we got e square over r and should be less than 1, right? So this imply r should be greater than e square, correct? But again, there's no option which says r should be greater than e square, so all of these are wrong. Now, let me move on to this problem. So what it says, r goes to r, there is a function which is infinitely time differentiable, and double derivative has exactly two distinct roots. Then which of the following cases could be correct? Okay. First option is the first derivative should have at most 3 distinct zeros. And can somebody tell me that as soon as you see this first option, you know it is instantly that it is the only correct option? I mean, it is of course just one correct type problem, but I mean, when you see this first option, you instantly know that it should be correct. Can somebody point out why?
Because if it has more than 3 zeros, then by Raleigh's theorem, f double dash will have greater than 2 zeros.
Exactly, yes. So if f dash x has more than 3 distinct zeros, then what will happen? Suppose a1, a2, a3 and a4 are 4 distinct zeros. By Rolle's theorem, because these are zeros, so between them there should exist some b1 such that double derivative at b1 should be 0. Again there should exist some b2 such that double derivative at b2 equals to 0. Again there is some b3 such that double derivative at b3 equals to 0. Correct? So in case there are more than 3 distinct zeros, the double derivative of f should have more than 2 zeros, but which is not the case. So it can have at most 3 distinct zeros. So f dash x can have at most 3 zeros. But what about other options? So suppose if can you find out some function such that f dash has no zeros and still f double dash has 2 distinct zeros, and it is little hard to find out. I mean, maybe you people can find it out little easily, but I tried it and I got some weird examples that I will give you. So for option B, you can just take your f dash x to be 2x square minus x. Please verify them. I'm giving you some count examples for other options and they will be very handy because and it took me really a good amount of time to figure out these count examples. So there's the count examples of B option. For C option, count example is if you take fx to be simply x times x minus 1 times x minus 2 times x minus 3, then your f double dash x become this 12x square minus 36x plus 22. And you can see that it has exactly two distinct zeros, but uh, fx has more than three zeros. So this at most three distinct zero option is also not correct because in my case fx has four distinct zeros. So option D can be tackled using this option. And I mean time is less, otherwise I would have showed you or verified these options, but I just insist you that you should try to verify them, that these are count examples to all of the options. In case of when you're doing the problem in exam hall, you got one option right, you should hurry up to the next problem because time is less. But when you're trying to do it conceptually, building examples, reading, understanding the theory, then you should also go to all the other options, even in the case of MCQs. Okay, let's go to other question. This is the next question. So it says, it is a very interesting question. So it says that a continuous function which is from real numbers to real numbers satisfies some condition that it is periodic with period 1. So that is that f of x plus 1 is equals to fx for all the real numbers x. What can you say about such a function? Is it bounded, not bounded, or if it is periodic with pi for some number, or it is periodic with pi for infinitely many x naughts? So this is what the problem is. Let's see. So can somebody tell me the option A? If you must have seen this somewhere, so can somebody point out, is option A correct or not?
Yes, option A is correct.
No.
Because we can only look मतलब अगर we can only look at 0-1 interval ना compact. Then
Yeah, so it is written f is not necessarily bounded.
okay. Sorry.
So it is incorrect, right? It have to be necessarily bounded. I got your logic. Yeah, so logic is correct. So what he's saying is that if I take some, say, any alpha belongs to R, and alpha I can bound alpha in the interval this, and using the fact that fx equals to fx plus 1, I can iterate it and this will be true for any n belongs to n. Okay, first of all, we know this. Now since alpha can be made inside the unit interval for any natural number n, so I can write this as n plus epsilon, where epsilon is less than 1 or greater than 0, right? Because alpha is bounded in such a manner, I can write my f of alpha in such a way, but now by using this iterated condition, this should be f of epsilon. So any value that it will give on any of the real number is same as the value it will give on the interval 0 to 1. Hence, so first thing is that. Now second thing is that if f is from this to this, or I restrict my function f on this compact interval 0 to 1, then we know that 0 to 1 is a compact set, or if you know, if you don't want to go in the compactness, just it is a closed interval. And in a closed interval, any continuous function is bounded. So any continuous function is bounded. Correct? So what will happen? So fx is bounded. Wait, okay. And I give you an exercise also, that if any such continuous function is there, such a function will be uniformly continuous. That you can also prove. But let me move on to the other options. So it is saying, can we have some x naught such that f of x naught plus pi equals to fx naught? This we need to answer. And for that, let me take some function, auxiliary function hx, which is equals to this. Okay. Now, first note that hx is continuous. Is the first thing. Second thing is that if I take some h of m, say, then it will become h of m plus pi minus f of m. Moreover, okay, so I forgot to define, let m be the supremum. We note that any function in the closed interval attain its maxima and minima, correct? So this supremum will be nothing but a finite value. Any continuous function in a closed and bounded interval attain its maxima and minima, and hence this m should be the finite number. And since values in the interval 0 to 1 or values taken in the whole real number are same because of the period 1, so this maximum will be maximum for all the values of fx in whole real number also. Got it? So let's take m to be supremum inside this, and let's take hm to be this. So I defined my hx function to be this. Now take hm to be this. You know that fm is the maximum value, correct? So f of m plus pi cannot be the maximum value. So f of m should be greater than or equal to m plus f of m plus pi. So this should be less than or equal to 0. Is this clear to everybody? Please ask doubt if you have.
Sir, here M is the point at which F takes the maximum, takes the supremum value, right?
Yes, yes, it is that point only. And note
Because
that,
you have,
yeah, note that we can also have this iteration and keep going. So it will take maximum value on many points. Yeah, now tell. Yeah. Hello.
yeah, because you have written M is equal to the supremum value.
In the case of closed and bounded interval, supremum value is exactly equals to maximum, right?
No, I'm saying that uh, it's misleading because you have written M is equal to supremum of Fx. But it is rather the
Maximum.
point,
Yours.
it is M is that
Okay, okay, okay. Yeah. I got it. Got it. Oh, okay, sorry. Okay, I should have said this rather. Yeah, correct. Because maximum is attained. Okay, let me correct. Yeah, thank you for pointing out. Yeah, it is misleading. M is actually the point where maximum is taken. Yeah. So because fx can attain maximum on 0 1, so there exists some m belongs to this such that fm is maximum. This is what you were pointing out, right? Correct?
Yes, sir.
Yeah. Yeah. Now this is correct. Thank you. So this fm can be taken as a supremum on this interval. Now we have this less than equals to 0. Now I can also have one point which is m minus pi, and if I plug in this I will have f of m minus f of m minus pi, and this should be greater than equals to 0 because fm is a maximum value, right? Now what is the obvious choice to use? H is given continuous, we have two inequalities. Our obvious choice is to use intermediate value property because hm is less than equals to 0 and this quantity is greater than equals to 0. So this implies there exists some c which is lying between this such that h of c equals to 0. Am I correct? I mean, I should say there exists c belongs to r such that this happens. Okay. In fact, this c will be in the interval 0 1. So that is not an issue. 0 1 or in r we can say interchangeably just because of this period 1. Okay. Now, okay. So by intermediate value property, and using continuity of h function, there exists some c such that s equals to 0. But what I define my s to be? I defined s to be f of x plus pi minus f of x. So it implies that f of c plus pi minus f of c equals to 0. This implies. So what we got till now is that we have at least one c such that f of c plus pi equals to fc. Correct? You have done till now. So what are the options? See. So if there exists a unique or there exists infinitesimally, this is what we need to decide because we have already pointed out that there will be some x naught. So the option that there is no x naught is over. Now we left with two options. Either there exists some unique x naught or infinitely many. Can anybody answer me? There should be
There are
unique.
infinitely many.
Why?
Because the m value of f at m is equal to f of m plus 1, m plus 2.
Yeah.
Because
So
it's a
it is because
periodic
of
function.
period. Yeah, good. So it is because of periodic function. We again can have so any say alpha n which is equals to c plus n where n belongs to natural numbers can satisfy this. Just because of the period, because this thing is nothing but fc and this thing is nothing but fc plus pi. Using this fact that I have written, right? Because of the period, fx equals to fx plus n for any n, and hence this alpha n will satisfy. It implies that, yeah, so this implies that f of alpha plus pi equals to f of alpha n for every n, and hence the only option left is the infinitely such x naughts. Correct. Any doubt? So this was a very nice problem, and see, it required the concept of continuous functions. They are bounded in closed and bounded intervals, And then we used extreme value theorem, which says that any continuous function in closed bounded interval will attain its minima, which is utilized here. Correct? And then we utilize intermediate value property to prove this. Okay, there's the proof. In exam you can apply some intuition also, that is not an issue, but yeah, that you should be but little rigorous with the answers. Okay, let's move on to the next problem.
Sir,
Yeah.
for the last problem, can we take the function as constant function?
For the last problem, we can take constant function. Yeah, we can take, because in any case it will it will be I mean it will follow all the conditions. Yeah, you can take. But that constant function will not provide you as a counter example to any of these options. Yeah, but you can, yeah, so you can actually deny the option uniqueness and there is no x naught. So B, C can be denied. Yeah, so B and C option can be denied using the constant function, but for other options you need to have this proof or some kind of intuition. Okay.
Okay, sir.
Yeah. Now we have this problem which says if f is again a continuous function from R to R, and we have this integral, so that 0 to 1 integral 0 to 1 f of x t dt equals to 0, then what can you say about the function f? Now again we'll use some properties of the integral and we'll see this. So let me do the change of variable first. So let me call u equals to xt, then changing the variable I will get 0 to x f of u du over x. Correct? For every x belongs to R, this is true as given in the question. Now this implies this 0 to x f of u du should be 0, because this thing is true for any x, right? So I can just multiply both sides by x, because integral variable is independent of x. So this means that this thing is 0 for every x belong to R. All right. And in case you are concerned about the case x equals to 0, then you can take limit x tends to 0, because you can't directly put x equals to 0, right? So you can take x tends to 0 limit, then apply this L'Hopital's rule and apply Leibniz theorem to see that f of 0 will become 0 automatically. Okay, so that should not be bothered. So 0 to x fu du is equal to 0. This is the fact we got. Now what we need to do is that, and this is true for every x belongs to R. So now, but then it will imply 0 to x, or maybe 0 to x minus 0 to by fu du equals to 0, which imply by to x fu du equals to 0 for every x comma by belongs to R. Correct? So it is 0 in any interval. Now if fu is not equal to 0, then there exists some u naught say such that f of u naught is greater than 0 or f of u naught less than 0. So I will just consider one case without loss of generality. We can pick this case. Now, f is a continuous function, and I will give you one exercise at this point, that if f of u naught is greater than 0, then there exists delta such that fu is greater than 0 for every u belongs to this interval. This you should do. So there exists one interval in which this function will take the positive value. If it takes the positive value in at one point, then it should take the positive value on some interval. And this is a property because of the continuity of f is given to us. And this is, I will write as an exercise. Please do it. And I guess it is given also as exercise in some Bartle-Shepard book. So yeah, there's the thing.
So why not the interval start from u naught minus delta?
Why not the interval start from? Okay.
It
Yeah,
can be centered at
yeah. Actually, the point is to prove that fu is greater than 0. We need to use just one inequality, one side of the inequality of the definition of continuity. So we'll require just one interval. In fact, I mean, yeah. So you can take this u naught minus delta also. Okay, there is no such problem, but I've used just this, so I've written this. Yeah, so you can take u naught minus delta also. So there will be this interval. This will be the open set where this will be open. Yeah, you can use this also. There will be no such problem that will occur. This is what I think. Yeah. So what will happen now? What I can take this interval. Now I can short this interval a little. I mean, let me just take my interval. Now in this interval, f attains maximum value. Again, we are applying extreme value theorem of continuous functions. So on this interval, f should attain maximum value. So let me take m be such value where x belongs to this x comma x plus delta over 2. Okay. Then, but we know that this thing, I should see. Okay, I have used u everywhere, so let me, sorry. Oh, yeah. So I used u not everywhere, so I should use u not u belong to fu. Okay, this is correct. Yeah. So this thing is equals to 0, right? This is what given to us. In any interval by x, this integral should be 0. So this integral should be 0. But on the other way around, this integral fu du is actually greater than I'm sorry, yeah, let me take infinite, my mistake. So I wanted to take attain maximum. Okay, so it should be minimum. Yeah, I'm sorry. So we are taking minimum at this moment, and I want to, and note that this minimum also will be greater than 0, because in the whole interval the f is taking just positive numbers, right? So in this, so this maximum should be also greater than 0, and this will become this which is greater than m times delta by 2. Correct? But equation 1 and equation 2. But second imply contradiction. Why? Why it is a contradiction?
Because
somebody
m
tell?
is greater than 0. Delta is greater
And
than
our
0.
delta is there exists delta greater than 0. Sorry. Yeah. Our delta is also greater than 0. M is also greater than 0. So these quantities can't be less than 0, right? But this equation will tell you that this is less than 0. A contradiction. Yeah. So maybe I should write this quantity is 0. So there is a contradiction, and hence so what was but it is contradiction to what? Our initial assumption, right? So initial assumption was this, that f of u not equals to 0. So then it will imply that f of u should be 0. Okay. Okay, let me move on to what? Next problem. This is a very easy problem. So we have given an inequality based on the difference of the function and difference of the variable. So what it is saying, so if yes is, so they are saying that yes is the set of the functions fx such that this fx satisfy this inequality. And it satisfy this inequality for every x and y belongs to R. Okay. What can you say about the functions that belongs to yes? Are they differentiable? Are they twice differentiable? Nowhere differentiable? What is the case, right? So okay, so let's analyze this inequality quickly. Sir,
Yeah,
till what time I can carry?
you can take up to 5 more minutes, I think.
Okay, actually I wanted to do a lot of question, but okay, fine, it's fine. So this is less than equals to x minus y. This is an inequality. This implies that so this whole thing is less than equals to x minus y. Now, if I take limit x tends to by both sides, I will get derivative of by whole square is less than or equals to 0, which imply f dash by is equals to 0, and since this is arbitrary by, so this should hold for every r. Now, if the derivative of some function is equal to 0 on all the numbers, what does that mean? First of all, you see that the function that I have taken is not given to be differentiable or something. But from this inequality onwards, if I take limit x goes to y, we know that this limit is existing because it is bounded and bounded by 0. So limit should exist and f dash by should exist, and such a f dash by is greater than or less than or equal to 0. So it should be 0 throughout. It implies f of by is a constant function. Now, just quickly, can somebody point out what are the correct options then?
Option D.
Option D, yeah. Any other?
Option A.
Option A, yeah. So only two options are correct. Okay, so on what question I should move? I need to see. Okay, so I should to some good problem. I had a lot of questions, but I couldn't. Okay, let me do this problem. That's it. Last problem we should do. So this is a problem which says, and by the way, when I will send the PDF, I will write all the solution and will send to you people so that you can read. I was not able to cover all the questions, but yeah, I will write the solution and I will send to you people so that you can read the solutions. Okay, so this is the question that f is given to be continuous function from an interval, open interval 1 to infinity to 0 to infinity, such that for every natural number n, fn is the smallest prime factor of n. So what is given to us? Fn is a smallest prime factor to n. What does that mean? So for instance, if I take maybe 30, then f of 30 will be 2. Why? Because 2 is the smallest prime factor of 30. If I take, for instance, take maybe 19, what is the answer? 19, because 19 is the prime number and 19 is the only prime factor of 19 and it is the lowest, and hence it is 19. This is how this function is given. I myself was not able to figure out if such a continuous function even exists, which takes lowest prime factor value on every integer. I tried to find out, but I couldn't find. So maybe this question is hypothetical in that sense, but let's see. Then which of the following options are correct? If the limit exists or doesn't exist, or and then they are asking about the solutions of some equation. Okay. So first of all, let's see that if I construct a sequence xn, which is equal to pn, where pn is nth prime number. So p1 is 2, p2 is 3, and so on. Then it can be easily seen that limit n goes to infinity, f of pn. So first of all, tell me what is f of pn? Can somebody point? Pn itself, right? Because pn is a prime number, I took. And now this limit will become pn. Now, how many prime numbers are there? Can somebody point out? There are infinitely many prime numbers, correct? And as n goes to infinity, this pn will go to infinity. So this is infinity. And hence, we get a sequence pn contained in 1, infinity, such that this limit is going to infinity. Hence, by sequential criteria of limit, limit do not exist. So I will just take 2 minutes and I will explain one more option and then we are done. So now we are asked about, so we got one option correct, that limit do not exist, and this option is of course incorrect. Now the set of solutions of the equation fx equals to 2024 are asked to us. Okay. So how many x satisfies fx equals to 2024? Yes, we are. And again, the continuity will be come in use, and I'm telling you people that whenever continuity and differentiability kind of thing is there, we have good tools of intermediate value properties, extreme value theorems, mean value theorem, and these things help us a lot in exam. These are one of the most important components of real analysis that we are using. In this case also we'll use. So let prime P greater than 2024. Now, because f of P is P itself, and what is f of 2024? Can somebody point out? What is the smallest prime factor of 2024? 2.
2.
Correct. Right? Now, what is f of P plus 1? Can somebody point out?
5.
No, it should be 2. Correct?
It's
Because P is because every
prime.
prime is a odd, and adding 1 will give you even, and even number is divisible by 2, so least prime that we get is 2. And this is a trick. So what happened? This 2024. Oh, I guess this is not required. Yeah. So 2024 is less than P, of course, and greater than 2. That it imply that correct. Now, by intermediate value property, and we know that f is continuous, there exists C such that C belongs to this interval P comma P plus 1 such that f of C is equal to 2024. Correct? But there are infinitely many primes P greater than 2024. So there will be infinitely many C, right? So there exist infinitely many C such that FC is equal to 2024. Got it? So this option D is correct. All right. Do anybody have the doubt?
Sir, okay, thank you, Aviral, for this nice session with a good collection of problems. I'm sure that the participants have really enjoyed this session. Now, it's time for interaction. So, dear participants, feel free to share your feedback and you can ask your queries regarding your preparations, if any. Yes. Yes, Gobika.
Hello, sir.
Yes.
Sir, my name is Gopika. I'm from St. Thomas College, Thrissur. Actually, I found the session really useful as I'm preparing for the JAM exam this year. There were some questions which I had already seen earlier, but I had some confusions regarding that, and they were all cleared by the session. Thank you so very much. Thank you, Vinod sir, for organizing the session. Thanks a lot.
Thank you.
Yeah, others, feel free to share your feedback.
Sir, am I audible?
Yeah, yes, well.
Sir, there is some net issues and there is some disturbance from the surroundings. That's why I'm not switching the video on.
It's okay.
Sir, Aviral sir, thank you for the great session. It was really interactive. And you paused and explained each question and answer in detail. So it was very nice. And you also gave some approaches about the questions, like if you get one option correct, then for the exam skip all others like that. So all of these were very insightful and hoping to attend more such sessions. Thank you.
Thank you.
Yeah, others, Aishwarya.
Good evening, sir. Am I audible?
Yes.
Sir, I found this session really interesting. It was a really different way of. It was really different from how I used to solve questions, and I got to know a lot of different proofs. So it was a really good session. Thank you, sir.
Thank you, Aishwarya. Think somebody raised the hand, I
Yeah,
guess.
Dharmendra is Dharmendra.
Yes, sir. I am Dharmendra Singh from Kasganj, UP. Am I audible, sir?
Yeah.
Yes, yes.
Okay. Uh, the session was very great and very interactive also. Thank you, sir, for this session. I want to ask about some real analysis related book used by you. And I want to ask about your PhD experience. Can you tell, sir?
Okay. Yeah, I will tell. So, analysis books, when I was doing my first reading, I did this Introduction to Real Analysis by Bartle Shevert. That was the good book. And then for when you do the first reading, and then you can do the second reading using Walter Rudin or this book by Tom Apostol, Mathematical Analysis by Tom Apostol, or you can use this book Walter Rudin. These are both good books, but it mostly depends on you which kind of book or which kind of writer you would like to have. Some people try to be very rigorous, some people try to be little motivating with the theory, and it depends on person to person. But two good books that you can approach is Tom Apostol and this Walter Rudin. One more thing is that one more thing is this if you're doing the first reading, you should try Bartle and Shepard. It is a very good book. Yeah. And PhD experience,
Yes,
regarding
sir. Yes,
PhD
sir.
experience.
Uh,
So
uh, Sir, for counter example, how to think about
yes,
counter example?
yeah, so I used
Yeah.
to, so when I was preparing for this GATE, NBHM exams and TFR exams, so there are a lot of problems that need good counterexamples. So this Kegzer, this book called Kegzer, problems in real analysis or problems in mathematical analysis. Yeah, so problems in mathematical analysis. They have 3 volumes, and book is one author is named as Kegzer. So you can search it and you will get it. So there are a lot of problems and solutions are given, and you have good counterexamples, so you can go for it and prepare it.
Yeah, I think it is published
Yes.
by AMS.
Yeah, it is published by AMS.
Okay, sir. Okay.
It's a very good book. And
Uh,
regarding PhD experience, it is very nice. Till now, I have started my research. Things are going fine. I get to learn a lot of very nice number theoretic results that are very mesmerizing. At the same time, I stuck in some problems for so long. It is sometimes frustrating also. So it is mix of both. So yeah, this is how it is going.
yes, sir. What is your PhD topic, sir, and how to do literature survey for any problem and find to gap between research paper or
So
key?
my area is very precisely, if I say it, is analytic number theory, and I also do work in theory of partitions. So these are the area that I work in. And about literature survey, first thing is that your advisor most of the time show you the direction, that this is the direction we are going to work. So then he give you the first paper that you want to that you should read. So you go with the first paper. Now when you are reading the first paper, there are a lot of references to the work that are done around that paper. You can go to those references, or you can see the work that is done around that paper. You can ask your guide that I am interested in this part of this paper, this particular part, and then you can go there. So this is how reading start, and this is how you keep going. Yeah.
Yes, sir. Can you tell, sir, first book for partition of numbers?
So there is this book by George Andrews. He is a very renowned mathematician, and especially in this area of partition theory. So you can read the that book, Theory of Partitions by George Andrews. That book is very good.
Yes,
Yeah.
sir. Okay, thank you, sir.
Okay.
Okay, thank you. Thank you, Dharmendra. Any others?
Sir, I have a doubt in the previous question, last before second question, where you uh,
Just let me see what was the question. Yeah.
let S be the
Last.
set of all functions.
Yeah, S be the set of all functions. Just a second. S be. I forgot the question. Fortunately, yeah. Now tell. Yeah. So S be the set of all functions that satisfy this inequality of right.
Yeah. So there, you took we were taking limit x tends to y, and then how did we know that f dash exists? Because you said we just got the inequality, and when we take the limit, we get a
Yes.
bound
Yes.
for it. How do we know it's
Yes. Yes. But the good thing with that is the bound is 0. That's the good thing about the bound. So what we did, we took limit x tends to y. So first of all, if I take limit x tends to y and I keep it like that, okay, so I will get limit x tends to y, f of x minus f of y over x minus y is less than or equals to 0. Correct? Actually, I should have written that step, that when I'm taking limit both sides, I will keep limit one side as it is, and on the other side it will be 0. Correct?
yes, sir.
So what will happen? That limit x tends to y, f of x minus f of y over x minus y is less than or equals to 0. So that limit itself is coming out to be less than or equals to 0. What are the options we have for a limit to be less than or equals to 0? Only thing is possible is that limit x tends to y, f of x minus f of y over x minus y should be equal to 0. But that limit is what? That limit is existing now because it is equal to 0. So this is existing and coming out to be 0, and hence function is differentiable because that limit is existing, and function is constant because that limit is 0. This is how it's done. I should have written one more step actually in between. Maybe I skipped that. Yeah. And
Got
it is the idea clear? Maybe if I will write the solution, I will write one more step. Yeah.
It is existing because the value is existing. It's not.
Yeah,
It is not just bound.
yeah, it is existing. Yeah, it is not just bound. Along with the bound, we have the bound to be 0. No other choice for the limit to go. Only the choice for that limit to be 0. And once it is 0, you know that it is existing, right?
Yeah. Got it.
Yeah, I hope that is clear, but still I will write that one line. Yeah. Actually, I think I went too fast with the question. I should have done some less question, but yeah, I'm sorry about that.
Okay, thank you, Madhuvanti. Could you introduce yourself, Madhuvanti?
Yes, sir. I have done my MSc from Pondicherry University, and I'm preparing for a PhD.
Okay. Okay, Madhuvanti. All the best for your preparations.
Thank you, sir.
Any others? There are a few more people, I think, very active in the discussions. Piyush Joshi, Roshika, if you have anything to add, you can. Okay, I think time is already.
Yeah.
Okay, anyway, thank you, Aviral, for this nice session. Yeah, I think you have prepared a lot of questions, and we didn't get enough time to cover all that. So it will be very better, very useful if you can add that hints and solutions and share it as a PDF. So we can share it with along with the recording of this session.
Yeah, I will just write the solutions of the rest of the question. I will send you the PDF and you can upload. Yeah.
Okay.
Yeah.
Okay, thank you, Aviral, and all the very best for your PhD. And I hope that you will be with math aspirants in future too, to help me in organizing this type of sessions.
Yeah, sure.
Okay, let us wind up here. Thank you, everyone. Bye. Good night.
And thank you, sir, for like inviting me to this session. It was very wonderful experience. Every time when I come up with something to teach or something, it also took me to some preparation. And I also revised few things. I went through some very nice problems. So it's been always great to be with the session. So whenever I will get time, I will just have one. Yeah. Thank you, sir.
Yeah, thank you. Thank you.
Thank you, everyone. Bye bye.
Yeah. Thank you, everyone. Bye. Good night.